Eliminating rival explanations, as it turns out, is one of the hardest checks we have to accomplish in our causal inference checklist. We're going to dedicate this whole module to introduce the basic theory of how to eliminate rival explanations and infer causality. So far, we have only been talking about the bivariate case of causal inference, where there are two variables of causal interest, where variation in x causes variation in y. But crucially, even though we have discussed the bivariate cases, the real world is multivariate. That is, for every interesting phenomenon, there are several causes, like probably in the hundreds or thousands. So it can't be just variation in x that causes variation in y. If this is hard to believe, just think about how many things cause you to become happy. For me personally, off the top of my head, hanging out with family and friends, exercising, eating good food, playing video games. There's definitely more than one. So if we live in a multivariate world, where there are many causes for a single effect, and our discussions on causal inference have been bivariate, where there is one cause to one effect, i.e., variation in x causes variation in y, you may be wondering why we even bother discussing the bivariate case when the world is clearly not bivariate. And the answer is pretty simple. We are unable to figure out multiple causes of a single effect all at once. To convince yourself of this, imagine hundreds of variables which are varying all at once, and your goal is to answer which variations in the variables caused a specific effect. Pretty impossible to do unless you start making grand assumptions. This is precisely why we restrict our attention to the bivariate case, and focus on one variable of interest, x, and its causal effect on another variable y. To show that x and y have a causal relationship, we need to think about how we can control for all other possible sources of variation. What do we mean by controlling for other possible sources of variation? Well, note that when we're trying to figure out whether variation in x causes variation in y, we have to make sure that rival explanations have to be ruled out. This was the non-spuriousness check we had to make to infer a causal relationship between x and y. And those rival explanations are variations in other variables that could have a causal effect on the variation in y. Let's group such rival explanations into a variable, w. So how can we rule out w in our analysis of the causal relationship between x and y? We restrict their variation, meaning we hold them constant. And this is important because if you can recall from an earlier discussion, we said that a causal relationship necessarily exhibits correlation, meaning that variation in one variable causes variation in another variable. If we don't allow w to vary, and we only allow x to vary, w cannot have a causal relationship with y, and any variation in y becomes solely attributed to the variation in x. In this way, we can show that x and y have a causal relationship, by holding all other factors constant. We call this concept of holding all else constant, or controlling for all other variables, except the causal variable of interest, x, and the effect variable of interest, y, the Ceteris Paribus condition, which directly translated from Latin means, all other things being equal. When thinking about causal inference, we should be very careful to note whether the conditions of our analysis are Ceteris Paribus, where everything but the x variable is held constant, such that variation in x becomes the exclusive cause of variation in y. The most direct and intuitive way to create a Ceteris Paribus environment is to conduct what is called a controlled experiment, also known as the scientific experiment. The controlled experiment establishes Ceteris Paribus by creating two identical groups of subjects. Those two groups we call the control group and the treatment group. What distinguishes the treatment group from the control group is that the treatment group receives a treatment, and the control group receives no such treatment. A treatment is any measurable change that we are going to induce in the treatment variable for the treatment group to affect the outcome variable. The outcome of the treatment group is the treatment outcome, and the outcome of the control group is the control outcome. How does this setup comply with our earlier discussion of causal inference? Of showing that variation in x causes variation in y? Well, the variation in treatment variable is the cause. Remember, one group receives treatment and the other group receives no such treatment. This is the source of variation in the treatment variable x. And the variation or difference between the treatment outcome and the control outcome is the variation in y. In summary, we have variation in the treatment variable and variation in the outcome variable, which enables us to discern a causal relationship between the two. This will become more clear with the upcoming examples. We're actually quite familiar with the controlled experiment, because we most likely tried one as part of a middle school science project. I think everyone at one point has tried the science project, where you're testing the causal effect of light on plant growth. If you're not familiar with it, it's quite simple. You create genetically identical plants by clipping one plant and taking the cuttings to grow them elsewhere. That way, we have plants that are all identical. Then you take some plants into a dark environment, and the other plants into an environment with artificial light. After some period of time, you measure the plant growth. If there are differences between the plants in the dark environment and the plants in a lighted environment, you conclude that the differences are due to sunlight. Why? Because these are two groups of plants which are identical except for their exposure to light. The plants treated with light make up the treatment group and the plants that are not treated with light make up the control group. The treatment variable is the exposure to light, and it can only take on two values, one where the plant is exposed to light, and the other where the plant is not exposed to light. And that's the source of variation in the causal variable, which we made the habit of labeling as the X variable. The outcome variable is the growth of the plant. We have two outcomes because there are two groups. The treatment outcome is the average growth of the plants in the treatment group, and the control outcome is the average growth of the plants in the control group. And that's the source of variation in the outcome variables, which we made the habit of labeling as the Y variable. Now we have variation in X and variation in Y. It seems like we are now ready to say that variation in X causes variation in Y. Are we all set to go? Well, not quite. We have to go through our causal inference checklist to be sure. Time order. Does the cause occur before the effect? Yes, because we measured the average growth of the plants, after we had already placed the two groups of plants into their respective treatment statuses, one with light and one without the light. Covariation. Is there correlation between the treatment variable and the outcome variable? Yes, because the plants treated with light grew more than the plants that were not treated with light. Significance. Is there statistical significance? Since we don't actually have any numbers to calculate significance, let's skip this one for now and assume that indeed the causal effect of light treatment is real and not due to chance. Rationale. Is there a reason behind this causal relationship? Yes, light is a key ingredient in the photosynthesis process which helps plants grow. Non-spuriousness. Is there non-spuriousness? The plants are all identical because they are genetic clones to control for differences between subjects of the study. However, there are still some possible confounders, if the lit environment and the dark environment are different in other ways besides the fact that one environment is lit and the other environment is dark. We would have to make sure that the temperature levels, humidity levels, soil quality, the pH of the water and other possible confounders are held constant or equal in both groups. Controlled experiments such as the one we covered earlier fundamentally require sameness of subjects like identical plants, identical compounds and identical climates. However, this is impracticable in the setting of social science research. And one big reason is because the subjects in social science are people, and we cannot replicate people like we can with plants, animals, molecules and chemical compounds. Furthermore, even if cloning people was not a morally reprehensible thing, experimentation on people is morally questionable. And as we will find out in a causal inference technique called randomized experiments, social scientists do actually experiment on people, but they do so after going through extensive checks to ensure that their experiments won't hurt people's lives.